Here we go. So we are still in 2-3. So this is just a really large section, so I split it in half. Okay? There's a lot in here. So what I just want to do first is we're going to talk about higher order derivatives. That's the point of this. Is we've only been looking at first derivative, and some people we've been talking a little bit about what if you did it again. Can you do that? Yeah, you sure can, and there are uses for those.
Why did you do 4 instead of 4 little things?
Because it gets to be a pain to draw that many little
What if
things.
you have 8?
Can you do that with 3 as well?
Yes.
Can you do
Can
Roman
you do that with 2?
like this?
Can you do that with 2?
Probably.
Sure.
Can you do it with 1?
So that's just notation. Notice, if you put without these parentheses on there, that means something different, right? That means like y to the 4th power or something else. Could mean other things too.
Wait, so can't you get like y to the 111th power mixed up with y, like the derivative 3 times? It seems like, I don't know, that's...
This is a you, Brett.
Primes are ticks, they're not vertical.
Okay.
There we go. Answer your question?
Yes.
Okay, so I wanted to tell you guys that when you find derivatives, you can find other derivatives. You can continue differentiating. There's not like a time when you have to stop necessarily, unless you hit like a sharp corner or something. So the questions are like, what about that? We're not going to do that too much, but let's just look at the notations. So you can keep doing this over and over again. So I'm going to put, what do you guys think I'm going to put in this last one? Dot, dot, dot. N. Excellent.
Wait, so Mr. McGee, what if you did it to infinity? Would that work?
There are reasons to do those kinds of things.
So you will.
So yes. So yes.
I wanted to contrast our notations. What other notations do we have for y prime?
dy dx.
Ah, dy dx.
And that's the line, and then whatever.
That's Leibniz's notation. What else we got?
Just to the little thing.
F prime of x. So can you guys write out the corresponding notations for these all the way down? Fill this out real quick. This is the first derivative. This is the second derivative, etc. Third.
We should do this. I just don't want to do it to the x.
Okay.
There's nothing there.
Now, do you guys know how to do this part?
I put dy over dy dx.
dy dx prime.
No, you put a 2
square.
by it. You put a 2
Put
by it.
twos. So here's how you do this. You go d squared y dx squared. Because the derivative is what's happening twice. You're not squaring y. It's like you're doing the derivative twice. That's why the squared is on the d part, which stands for derivative. Does that make sense? It's a little bit awkward. So Leibniz's notation for this isn't as good, I don't think.
Well, then why do you do it on the x on the bottom? Not the d.
It's a good question. I don't really know. I'd have to think about it. But it goes there on the bottom. It's a good question, though, Austin. I can't remember. So like that, dot, dot, dot.
Yeah, that notation's weird.
Depends what you're trying to do. Like when we do problems like that, you guys saw me using this on the last problem before, right?
Where you need to plug in.
It's really nice for those kinds of problems. Yeah, it depends if you're using just 2 things. As soon as you go to 3 things, it's much better. So as soon as we introduce time,
You're going to one.
And derivative.
that's a lot better notation. Dx to the n. Right here?
Oh, you put a y. Oh, that's instead of a y. No, it's supposed to be y. That was just Mr. McGee.
Bad, bad, bad. Sorry.
Hey, I'm nice and do with the eraser
Okay.
end.
Let's talk about
Right?
what these represent physically. I mean, just one of their possible interpretations. There could be lots of different ones, but the most common one that has been used time and again for hundreds of years is we said, what's the first derivative represent physically? What's one of the things?
The slope of the tangent line.
Yes, but as a physical quantity in the real world.
Not the slope of the tangent line.
So you're right. First derivative is velocity. It comes from taking the derivative of position. We usually call position. In physics or in here, most of the time you refer to it as what's position? Like, what do we call its function? S of t. That means this is s prime or v of t. You call it s prime. So when you see s prime, you should be thinking, oh, that's velocity, right? And then second derivative means acceleration, which is s double prime or a of t.
Is S of t.
Okay. Now, maybe if we kept going, there'd be stranger ways to think about this. But this is really common. Like in a physics 1 class, you can use.
So what
it
is
all
the
over the
3
place.
represent?
That's what I'm saying. Maybe it does mean something, but
Do you know?
I don't remember off the top of my head. I think it does mean something though. We'll talk about it. We're gonna have a little motion detector. We'll do some stuff with that soon. Okay.
Motion detector?
So we'll run around the room. We'll plot it with a motion detector on our calculator. See what happens. Okay.
Turn the lights off, so there's a cat.
What?
Okay, you don't have to look at
I don't get it.
I don't get it
Yeah, what is
either.
it?
Is that Lucy cat?
it. Yeah, I turned the lights
Oh,
off. So there's
I forgot.
I think it's an emotion detector.
No.
You're like, oh,
So, did you guys see that f sub n of x, like the nth derivative? I just wanted to give you an idea, like why would you ever need an nth derivative? And I gave you 2 of these problems in the assignment. They're tricky. You have to figure out the pattern and then relate that pattern to x. So when you try to figure out an nth derivative, how do you do it? Do you just go straight to the nth derivative?
No.
You got to take like derivative 1, derivative 2, derivative
And then
3,
you're seeing
and you
what's
got to
happening.
keep doing it and try to figure out a pattern and put it back in terms of n. So this can be a difficult process. It's not part of this year's class, but it is really important in mathematics. So let me just give you an idea. Your calculator, when it graphs something, does it have access, like when it graphs x squared, does it have x squared and all the points on x squared stored in the calculator?
No.
Is it finding
Is
the
it possible to
derivative?
store an infinite number of points in any computer, no matter how powerful?
No. Not
Why?
even Moore's laws will let
Because
that happen.
it's infinite. You
How does
remember.
how do you remember an infinite thing? How does the computer remember an infinite thing? A computer says, take thing, do stuff. It can't remember an infinite amount of stuff. So how does a computer, like how does it get your functions in there?
It has a couple of primary functions and ways it solves that it uses.
But it can't store any infinite number of things.
So it uses the derivatives.
It uses derivatives, yeah, definitely. But it can only store a finite number of things. So one place where you'd use this is all computers that ever use any kind of mathematical relationship. If they want to graph a function like f of x, they can only use a finite number of points, right? Some computers are more powerful, so they can use more points, but still finite, okay? So you can't just put in x squared, and the computer doesn't say, oh yeah, I know exactly what all those infinite number of points look like. It does what's called a Taylor expansion. That's the sum.
We've done those before.
Yeah, we've seen this notation a little bit. This is more Calc 2. This is toward the end of Calc 2, after you've done a lot more stuff. But what it does is it holds a finite number of things in its head. How does it do that? It takes the nth derivative and it takes it C, puts it over a factorial. There's more n's in there, right? So you guys can notice that right there we have the nth derivative, right? So what this guy is this is a sequence. It's a complex sequence. It's got derivatives in it, but it's a sequence of stuff, okay? So what this does is it takes the sum of that sequence, and when you do that, you get what that function would look like. So it can only take a finite number of things, but it turns out that some sequences, when you sum them to infinity, they settle down. and they behave the same way. So let's look. Let's
Like,
just
yeah,
look at
well,
this
like,
real
what
quick.
if you did x squared in that? Like, what if...
Let's do one. So what's e to the x look like as an infinite series? So you could build it by doing this kind of thing. Let's look at it. So can somebody look in their index and find what's called a Taylor expansion? Look at it. Taylor series. Index. Quick. We don't have much time to waste. Taylor series, please.
Like,
Let's see if we can find e to the x. I kind of remember it, but I might be wrong. So
I'm on Green's theorem.
I haven't used it for a couple years. 676.
Page 676?
So let's see if we can find the Taylor expansion. That's what this is for e to the
Oh, look, I
x.
think I found something.
You said the Taylor series.
Taylor series, yeah. It's on page 677 when I just showed you. And I'm trying to find e to the x. I see sine of x. No.
Do you want this one?
Page 682. So,
Oh.
someone a long time ago named Taylor figured out that this is the way you could input infinite things, make them finite, and enter them into software. And he did this before there was software for other reasons, but now we use it to put stuff into software. So if you see all those common functions on the left there? And you see their series expansions. So e to the x, how do you write it? It's equal to
1 plus x plus x squared over 2 factorial.
So we see our factorial, this is where it's coming from. Plus x cubed over 3 factorial plus, it's got pluses on all these, no minuses? Sometimes they alternate. Are they all
They're all
pluses?
pluses.
Okay, x fourth over 4 factorial, etc. So the question is, how accurate do you want the thing you put in your computer to be? If you want it to be really accurate, how many of these terms do you think you need to use?
A lot.
As many as possible.
A lot. If you wanted it to be exact, how many of these terms would you need to
Infinite.
use? An infinite number, because it says the function is exactly equal to this sum up to infinity. But if you want something that's decent, you might only use the first 5 terms, and guess what? You can put 1 in, if you wanted to put like e to the 2nd power in there, then you could put 2's in those x values, and if you just stopped right here, you'd have a finite thing. And your computer can memorize that, and it can remember that, and it can use that. You guys see what I'm saying? So this nth derivative thing is definitely useful, just a little bit.
So like, how would you do x squared?
So how does this become this? How do you
Yes,
get this into
yes.
this? That's something for Calc 2. It would take us quite a while. Really cool. That's like one of the last things in Calc 2. And I'll tell you, my Calc 2 teacher at the university, she barely did that. Like, and people complained a whole bunch, right? Like, people were like, oh God, this is so hard, blah, blah, blah. And I was like, please do more, because I knew I was going to need it. And then when I got to Hong Kong, guess what?
You needed it.
I didn't just need it. Like the Chinese people that were working with me, they were like, oh, this is just a Taylor expansion. Blah, what is I working with? I was like, oh my goodness, this is like, I slow down. And then I had to, like, that week, I went back and I learned how to do Taylor expansions really, really well on my own. So, big time important topic in engineering and mathematics. This was engineering I was doing. So, pretty up there. Okay, let's do a couple examples. We'll be done. So let's say we've got f of x is this. So, whenever your teacher, especially if you have people in your class who are like, oh, complain,
Don't let them get away with it.
if they get away with that, what could happen to you?
Fail life.
Something in your real life could be bad later. So.
You'll be killed.
Don't let those teachers do that.
Okay.
Okay, let's take the first few derivatives of this. You guys can handle it. That's easy. F prime, what is it? Somebody help me.
28.
Oh my god.
I even wrote the other one.
Minus 2 cosine, it stays minus?
Yeah.
For sure?
Yes.
Okay. F double prime.
28 times 3 is 56. It's 94.
Do 30 times 3 is 90 minus 6.
Okay, that works.
Plus or minus? Kyle, tell me. Plus or minus here?
Plus.
It's 84.
It's plus.
Oh, so there's
Is it
going to be a
84,
pattern.
not 94?
Yeah. 90 minus 6.
Sine
Oops.
turns into, well, look, the cosine x turns into negative sine x, so it turns into negative sine x, yeah.
So then when we get 2 times 80 is 160 plus 8, 168 minus or plus? Minus.
Wait, no.
Shouldn't it be sine x?
No, because you're taking cosine to
Oh,
sine.
yeah, it's negative.
Yeah.
So
Yeah,
oops.
okay.
I'm getting too excited. Is this plus or minus? When you take the derivative of sine, it stays.
It's minus
So
or
the derivative of sine is cosine. Yeah, cosine is negative sine. That's what I get.
So, would it be possible to keep going and develop the nth derivative? Yeah, I think so.
Well, okay, so
We'll do one of
what
those.
would-
You're gonna
what
end
would-
up with
can
just
you do one more?
168.
Show us what you do one more.
It'd be
Yeah,
168.
So eventually you're just going to get either
Two.
between sine x, 2 sine x, or
Minus
No.
negative.
Yeah, eventually what's going to happen?
It's either
It's
going
gonna
to
flip
sine
back
x,
and forth between
cosine x,
two.
or
These are
Yeah.
going to flip. Could you build that into a pattern with n?
Yeah.
Yes, you could, and I don't even think it'd be that difficult. I'm going to show you one tomorrow. Okay? But what's going to happen to this part eventually?
it's just going to
It's going to go away to 0, right? After this term, the next time it's 0. But right now we're going to have a minus 2 sine x, correct? Okay. Easy, right? Let's do the same thing on this one. So let's do it with the other notation just to practice. E squared y dt squared.
Too much.
4t minus
14?
plus 4.
I better rewrite this, right?
I might change my t's to x's.
Don't.
I hate
You're going to have to get used to other variables.
hate the t's.
It's going to be big in chapter 3.
They do.
Okay, this guy,
Plus 4 over t.
4 over t squared. I'm going to leave it like that because we're going to do it again, right?
Wait, I don't.
Plus 4
Secant squared
secant squared
t.
g. Okay. Let's do one more.
dt cubed equals
I think this is the last one.
minus 8t cubed.
That part wasn't bad. Okay, let's be careful.
You're going to have to do the quotient.
We're almost in new territory here that we don't know how to handle yet.
Can't you just go secant squared tangent squared because there's no negatives with the secant?
I think that you can write this as secant times secant, and that's the only way you can handle it yet now. There's a faster way, which we're going to learn tomorrow, or Thursday. Okay? So I have to use the product rule, right?
Okay, so that goes into secant.
Secant tangent.
So I'm going to go plus 4 and keep going. I think it's going to be a little bit lengthy. There's a fat shortcut to this, which we'll learn.
So wait, as in this is gonna take a lot of space because I'm on the edge of my paper.
Why? Because it's a product rule.
Yeah, so it's gonna take forever.
So first thing, derivative of second thing, what's the derivative of secant? Secant tangent. I love it. Plus, second thing was also a secant, and we also get another secant tangent for the derivative of the other secant, right? So when I simplify this, I get minus 8 over t cubed plus 4. Isn't that the same kind of thing? Is that exactly the same? 2? What is it?
Secant
Or you can do
2 secant
squared
squared t
tangent.
plus
tangent t.
Yeah.
Is that clear? Do we have questions? I think we can all handle that. Questions? Because I think we're going to stop there for today.
Are we getting a new assignment? Question.
Yeah, let's do Thursday. So I will do 2 more examples tomorrow. I'm going to do like one where we look at some graphs. So look at some graphs and go back into the graphical mode and how to interpret that a little better because I haven't shown you guys that much. And then I'll do an nth derivative. Alrighty? So where is this one?
Okay.
This chapter, remember guys, this chapter as a whole, we're just learning our derivative rules. Austin.
Sorry.
As a whole, this chapter is learning our derivative rules, learning how to mechanically do them, then we're going to start applying them a bunch in the next chapter too. Okay? So we're not doing a whole bunch with them yet. Looks So in that same section, we're gonna do 99 to 120 and
I didn't even recognize you.
125 to 135.
It's probably good.
Kyle.
Okay?
What if you just like grab my shirt, the sleeves like rip my shirt?
So I'll show you guys a couple more things tomorrow.
Rip it out.
It's not very short. It's 21 plus. It's not bad.